आता सर नाही मला ते बघता येत नाही, क्लिक केलं तर स्क्रीन पुढे जाईल. तर आता अजून 26 पार्टिसिपंट आहेत. 5 मिनिटं थांबूया. पार्टिसिपंट नंतर केलेलं तर मजा नाही येणार. You take a call and tell me on WhatsApp. चालेल चालेल. 9:45 पेक्षा आपण जाऊन बघूया. तर आपल्याला 9:30च्या पुढचा काउंट
Good morning, participants. We will start within some time, 5 minutes. Okay.
Thank you, madam.
Good morning to one and all. Good morning to one and all. On behalf of...
Good morning, madam.
Sir, yeah, good morning, sir. So shall we start?
Yes, yes. Govind, sir?
Oh,
Yes,
Hello?
sir. Go ahead. Go ahead.
Yeah.
Go ahead.
yeah. Good morning to one and all. On behalf of Sardar Patel Institute of Technology and myself, Dr. Reena Sonkusre, a very warm welcome to all my participants.
Ma'am, you're not audible.
मैम आपका आवाज नहीं आ रहा है रीना मैम
Okay. Yeah. Now it is coming.
yeah now it is audible
Sir, music stop कर दो.
मैं कब का स्टॉप किया स्टॉप
No, it is not stopped.
Yeah, it has stopped, ma'am.
no
Yes.
it
Now
has
it is
stopped
stopped.
it has stopped ma'am
Okay. On behalf of SPIT and myself, Dr. Reena Sonkusre, a very warm welcome to all of you at 4th International Conference on Communication, Information and Computing Technology Conference 2021. Industry-sponsored tutorial session, Foundation of Reliable Embedded System. Let me take a moment to talk about the first speaker of the day, who is certified by Safety System UK up to level 1 to conduct safety certified program in the embedded system domain. And he is interested in microcontroller, microprocessor architecture. Some of his valuable contributions like worked on ARM architecture for Cortex M3 and Cortex M4 core. He worked on 8085 and 8086 Intel architectures. He worked on developing systems using Keil or Code Composer Studio IDE. He is comfortable in using Texas Instruments parts for the ARM architectures. He likes to train people in the embedded system domain and delivers hands-on session. Currently, he is working on time-triggered architecture for embedded system with MSP architecture from Texas Instruments and on 8051 core from Silicon Labs. It is my privilege to welcome an embedded system passionate, Mr. Govind Gaudalkar, an engineer at Microwave Devices Technology. I request Sir to please share his thoughts on today's topic, Foundation of Reliable Embedded System. Over to you, sir.
Thank you, ma'am. Good morning to all.
मैम shall I stop sharing
Yes, sir.
okay गोविंद सर आपका भी आवाज थोड़ा कम आ रहा है can you increase the volume शायद मुझे कम आ रहा है I don't know you can ask the I'll ask the participants
Can everyone hear me clearly? Am I audible?
Yes, sir. Yes, sir. We can hear you.
Very clear, right?
Yes, sir. Yes, sir.
Yeah, that's great. Okay. So let me start off with a great thank you to SPIT and the conference team at SPIT for inviting us for this tutorial session on foundations of reliable embedded systems. My name is Govind Gaudalkar. I would be your I would be the trainer, or you can say I would be conducting this tutorial for this entire day today. I lead Microdevice Technologies. Microdevice Technologies is based in Mumbai. It was established in 2005, and ever since that, we have been working in the field of embedded systems and related domains. We are the authorized and a sole partners, training partners of Safety Systems Limited from UK. Safety Systems Limited was founded by Dr. Michael J. Pont. He is the CEO and founder of Safety Systems Limited. They have a lot of patents in the domain of time-triggered architectures, and they have been doing some amazing work in the field of electric vehicles and medical
Looking
domain.
good.
And they basically deal with safety
बघ
critical or
ना.
mission critical applications. So what you're going to experience today is not
Yes.
the general embedded systems architecture that all of us
Eh?
over here are aware of, and all of us that we work on. That is, most of us over here would be working on event triggered architectures. That is not the subject matter of today's talk. It is going to be the time triggered architectures. And very soon, you'll come to know what these architectures are and how they could be useful in safety critical domains. So I'll just be starting the screen share now. I hope the screen is visible to all, the welcome screen. Hello.
Yes,
Yes,
sir.
sir,
It is
it's
visible.
visible.
Yeah, that's great. Okay. So Micro Device Technologies presents safe and reliable code for embedded systems with a case study of washing machine controller that we would be seeing towards the end of the day. Now, how are we going to go about this entire day of this tutorial? So the first and foremost, we would be introducing you to the time-triggered architectures. By TT, I mean time-triggered, and the different international standards for various segments. That is the various standards that are required for the products to be certified to be sold in the international markets. All the international, some of the international standards which are really needed for making these systems, saleable in almost all markets across the world. Then we would have examples running on the Keel simulator. Now we have a mixed bag of people over here. Like there are people from the industry, people from academics, students. So to accommodate all the different kinds of audiences that we have today in this seminar, we have decided to choose 8051 as the target for most of this session, for a simple reason, so that it becomes, the architecture becomes more understandable to everybody, that is all the audiences. Otherwise it is that we generally do all our seminars, all our trainings on the ARM derivatives, the ARM Cortex MX derivatives. So that is what we are going to do throughout the day. Then we have some interesting things also lined up. There will be one quiz at the end of the first half of this session. After that, we will have a break, the lunch break. And then at 2 p.m., Dr. Michael J. Pond, the founder, CEO of Safety Systems Limited, who is the creator of this technology and who has actually pioneered time-triggered architectures and created some amazing technology that is actually used in the industry, in electric vehicles, it is used in medical systems, it is used in industrial systems. We'll show you what kind of work they have been doing, and they are actually also going to be creating some standard time-triggered architectures, which along with Exida Systems, which is the world leader in these international standards. Then after the talk of Dr. Michael J. Pond, we'll continue with some more examples on TD architectures. Then towards the end of the day, we will have the second quiz. So in all, there would be 2 quizzes, and the quiz marks would be totally, that is, quiz 1 is for 10 marks, quiz 2 would be for 11 marks. So the total tally would be 21 marks. And what is it in there for you for the participants? So Micro Device Technologies is going to select the top 20 candidates who performed well in both the quizzes. The top 10 candidates will get to take a live 10-hour course on software design for embedded systems using Keel Simulator, and that would be absolutely free. The date and time of the start of the course will be mailed to the candidates on the email ID that is provided by the candidate at the start of the quiz. So you have to put your correct email ID in the quiz form before the, of course, this would be a Google form that we would be sharing with you. And you have to put your name and your email ID so that in case you win, you should be we should be able to get in touch with you and inform you about the date and time of the course that we would be offering you free of cost online. It is only that we expect that the candidates should make themselves available at the scheduled time for taking the course. Course dates and times are at the discretion of Micro Device Technologies. Then the next 10 candidates who have topped will receive an STM32 Nucleo board from having a ARM Cortex M3 processor. So that is for the next 10 candidates who win. So just gear up and listen to what this tutorial is all about. It would be, the quizzes would be based on entirely on the tutorial that we are going to conduct. So you just have to be careful in listening to all that is happening here and observing all that is going to happen here. And so gear up and get a chance to win either of the giveaways, so that we have tried to maximize the scale of the pandemic, and we thought that we should really share some more goodies with you for having attended this conference and this tutorial, which is one of its kind. I'm pretty sure you must have not used many of you must have not even used TT architecture. And then we have some more things also lined up. Of course, one more important thing, all the participants who score a total of 15 marks and above out of 21 in the two quizzes will get a participation certificate. So you have to strive for that 15 mark threshold so that you get a certificate of participation. And the announcement of 20 winners would take at least 5 working days so that we can compile the winners properly. And these e-certificates would be given to the successful participants, and they would be mailed after 5 working days. And one final thing for all the participants who attend the tutorial for the whole day will get a 30% discounted exam voucher from Linux Professional Institute of Canada for taking the certification exam on Linux. These details we would be sharing at the end of the day. So all the participants who have attended the tutorial throughout the day will get this this voucher as well for actually taking up the Linux certification exam from LPI Canada. It's one of the leading certification providers in the world, which are vendor neutral Linux certifications. So that is up for grabs. And I think this is how we are going to proceed for the whole day. So just fasten your belts and be ready for all these goodies and some amazing technology that you'll come to know throughout the course of the day. And the biggest attraction for the day would be the talk by Dr. Michael J. Pont, who is the creator and the patent holder for this amazing technology that has been created, which is used right in all the critical domains, from medical to railways to automotive to industrial. It's everywhere where safety and reliability is the key. So it's not just about creating a normal, we are not going to deal with normal embedded systems in which you generally create some kind of, you have some Arduino working, or you have some kind of small little system like a robotic system. We are going to focus on the architecture design. And this is all about, scheduling, making your system safe, creating your own schedulers. So this entire, the track of time triggered reliable systems that we are going to talk about is all about that. And there are also certifications, international certifications, in which you can get yourself certified through us, that is Micro Device Technologies, to work with technologies created by Safety Systems and be ready to take the challenges in the world, and some of the best of employment opportunities will open up for you in the entire world, so in this domain. So it's great that you're getting a chance to witness this technology at this conference through this great conference of SPIT. So let's start off now, and let's get on with our actual work. So I hope you have understood how we are going to go. Focus on the tutorial so that you can answer the quizzes and win the goodies, which are really a great way to start into this particular domain. Yeah. So are we ready? All set? Okay. So what is, yeah, somebody said something? Yeah. Okay. Safe and reliable embedded system. What is it? What is an embedded system that we say is safe and reliable? A safe and reliable embedded system is the one that determines at runtime that it has entered an abnormal platform state. One or more system requirements are not met, and this causes a system damage. And it can handle this situation in a manner that reduces the risk of uncontrolled system failures. So basically, what we are saying is a system that will determine whether it is in a state that could be a state that could not be a very pleasant state for the system or for the users of that system. That means it's in an abnormal state, and it's called the abnormal platform state. And one or more system requirements. And why does it really get into this state? The reason for that is one or more system requirements. That is the very specifications that we had set out with the system. One of them has not been met for some reason, and that particular requirement, if it is not met, it could cause a damage to the system, or damage to the, or some kind of damage to the people who are using it, which could be a catastrophic situation. So such a system, if it enters in such a state, it should be able to handle the situation in such a way, or in such a manner that will reduce the risk of uncontrolled system failures. That means it could be such that because of a particular failure, there could be cascading effects that could cause some really catastrophic behavior, or really a dangerous situation for the users of that system or that system itself. So safety and reliability of an embedded system is very, very critical. So how to actually make it safe, how to make it reliable, you have to really have an architecture or a software design that will ensure that it becomes safe and reliable, and you are able to determine the current state of the system, or what is the current state of the system. You should be able to really know what state your system is in. So the safety and reliability aspect of an embedded system is really, really critical. So techniques for development of such kind of reliable embedded systems are of great concern in safety critical markets like automotive, medical, rail, aerospace. where uncontrolled system failures may have fatal consequences. It means like, if you are driving a car at a high speed on an expressway, and there is some kind of a system failure that has occurred within the car, and the car has really malfunctioned in a way that it suddenly stops if it's in the cruise control mode, or it could be anything that could be really dangerous for the occupants of the car. If there is a medical system, like say you have a ventilator system that is not functioning, properly at a particular time, but at certain times it's not functioning up to the mark, these kinds of systems can cause death or even permanent disability to humans. So you should really, your system should really be able to detect that it is really in a state that is dangerous, and it should be able to take some kind of a fail-safe route to actually ensure that there is the occupants or the users of that system are safe, or at least the damages should be minimized to the greatest extent. And the same applies to railways, the same applies to aerospace sector, where you are flying in an airplane and there is suddenly some kind of a failure in one of the subsystems of the plane. That does not mean that the plane just comes down. You should be able to try to put the system in a fail-safe mode so that you can safely either land the plane, or you can take some corrective measures till you reach the nearest airport, and the occupants of that particular airplane are safe. So such kind of systems are, the design aspects of such kind of systems are extremely crucial, and how you make them and how you make them safe is very, very critical. And time triggered systems are the best way forward when it comes to such kind of system design. So the growing challenge of developing such complicated embedded systems in traditional safety markets resulted in the emergence of new or updated international standards and guidelines. Like, if at all you are developing such kind of a system, that has to be a system that is reliable and safe, and it qualifies to be sold in the international markets. It is always essential that your system design meets some of these standards depending upon the sector in which it is going to be used. So if it is an industrial system, the international standard that your system should really adhere to is 61508, IEC 61508. That's for the industrial. The automotive sector requires the ISO 26262 standard to be adhered to. Then software, whenever you are creating software systems for the aviation or the aerospace industries, you should really meet the D0178C standard, which is the international standard for softwares and airborne systems. The medical systems require 60601. And there are just some standard coding guidelines when it comes to the C programming language. And this has been standardized by the MISRA organization. It's Motor Industry Software Reliability Association. That is what it means, MISRA C. So MISRA C is the standard that needs to be followed. That is, you should write code that adheres to these coding guidelines. And it is generally a very good practice to write C code that adheres to MISRA coding guidelines, so that you can make your systems safe and reliable and eligible to be sold in extremely in those markets or in those countries that are very, very particular about the safety and reliability of the system, and in general, the safety of the users or the occupants of that system. So simple household appliances, just to give you some examples, simple household examples need to address safety concerns. For example, manufacturers need to ensure, now I'm talking about a washing machine that we generally use at home. So whenever it comes to washing machines, I'm talking about the front loading washing machines here. Manufacturers need to ensure that the door of the washing machine cannot be opened by a child during a spin cycle, and must do all they can to avoid the risk of fires and always on applications like fridges. Refrigerators work 24/7, 365 days. So there are chances that the hazards of fires are always there in such appliances. So the design of such systems should be like they should not catch fire at any point of time. They may shut down, they may stop operating, but should not have any kind of fire or any kind of an explosion in the compressors, so as to protect the users of that system. So all these are basically examples of embedded systems. Like, embedded systems are everywhere around you. It is ubiquitous. It's everywhere. You just can't see them, but they are everywhere. You could say even on your body, you have an embedded system in some form or the other. So this is one industry, that is everywhere, almost everywhere. And it's only that there should be right kind of engineers available to make these systems. And if it is so much of, available almost everywhere in all spheres of our life, I don't see why there should be there should not be any good job opportunities. It's only that the skills are lacking in the people, but the jobs are abundant in this field. But it appears the other way around. There are no jobs, and in this field is what people keep telling me. But there are jobs. It's only that you don't have the skill sets to grab those jobs. So that is how it is really. That is the sad part of it. So when you are in the embedded domain, you should have the right knowledge to actually get the niche jobs in this sector all over the world. There are abundant. So it's only that you should have those skill sets to actually grab them. Yeah. So there are some standards like the IEC 60730 have also emerged in these kinds of household sectors where such kind of systems are developed. So when we are talking about reliability, it's not just about the safety in any sector. Reliability does not mean only safety. Safety, of course, safety is of paramount importance when it comes to the users and the occupants of a particular system. But reliability provides safety, no doubt, but it has some other goodies also attached to it. One of the biggest advantages of reliability from the manufacturer's point of view is if they can claim reliability of their system, that will ensure that the products that they make, the amount of spend that they're going to do on a product is drastically reduced. Because if their product is reliable, naturally, what warranty that they give or they offer, that warranty is not going to be affected, and they don't need to really spend money on the repairs and the replacements of such kind of products. And that is what affects the company bottom lines a great number of times. If the product is not reliable, there would be great number of returns and great number of repairs that they need to do during the warranty period, and it directly affects the company revenues. So if a manufacturer is able to demonstrate that the product is reliable, their warranty related costs that they have to bear will be reduced drastically. So there would be minimal product recalls, and because of the high reliability, they will get repeat orders. Now, you must have read in the newspapers many a times, Many of these automotive companies do recall the vehicles for some faulty part and some kind of a fault in some kind of a system within the car. And this recall is all over the world. So imagine the amount of spend that they have to do just on on fixing up the problem. So that affects their revenues to a great extent. Imagine if it was detected right at the design time, or maybe during the production of regarding some kind of a fault in some kind of a system, the company would have saved millions of dollars on such kind of recalls of products. So reliability helps manufacturers as well to actually maximize their profitability of the product. So now when we are talking about time triggered systems, in short they are called as TT, time triggered systems, and event triggered systems are ET systems. So what is the fundamental idea behind a time triggered system? So the implementation of a time triggered system starts with a single interrupt that is linked to a periodic overflow of a timer. So what we are saying is we will have one interrupt in the system that is directly linked to the periodic overflow of a timer. That means that we will set up some timer that would overflow at a fixed time, and we would use this as a starting point. And this interrupt that we have, that I say that that the timer would overflow at some, say, at around 5 milliseconds, and there is an interrupt that is generated every 5 milliseconds that the timer overflows. This can actually be used to drive a scheduler. So it is a simple form of an OS. A scheduler is nothing but a simple form of an operating system. And this scheduler will then release tasks at predetermined points in time. So what we are saying is there is a timer that is overflowing at a fixed time, and we are using an interrupt. And whenever that interrupt is raised, the scheduler will actually release the tasks. That is, what are tasks? Tasks are just a simple example of a task, maybe the blinking of an LED every 5 ms, to just make things simple. So that is a task that it is performing. And every 5 ms, the LED should really perform the blink. And if I need to do this, I can really have a simple a timer based overflow, which actually overflows at a particular rate, and a particular task is called at whenever the timer overflows. So we are actually making the task release whenever the timer overflows. Now this is the starting point of a time triggered system. We will see this in practice, how it is done. We are going to see some examples associated with all this. So a TT architecture can be viewed as a subset of a more general event triggered architecture. So we can say that time triggered architecture is really a subset of an event triggered architecture. So what does that mean really? When we are working with event triggered architectures, we are actually working with multiple interrupts, which is what we all are familiar with. We use different interrupts, like there could be one interrupt which actually detects whether there was some kind of a character that was there in the buffer of the serial port, or there could be an interrupt that detects that there is some kind of an event, or an analog to digital converter has to capture an analog signal and convert it to a digital signal, digital equivalent at a given point of time. So all this, I mean, when you have a system with so many different kinds of interrupts, you can have different peripherals that actually are implementing these interrupts and actually giving the larger system operation in general. So implementation of this event triggered architecture involves use of multiple interrupts so that your system can respond to a particular peripheral which requires service at a given point of time based on the interrupt that it has raised. So each of these peripherals are then associated with periodic events that may be occurring externally to the system. Now, these events that are occurring externally to the system that are actually triggering the interrupts, these are physical events. They are stochastic in nature. You have no control on them. They could just come up at any point of time and an interrupt is generated. So we can say that, the implementation of the ET architecture involves use of multiple interrupts, each associated with specific periodic events such as timer overflows. So these events could be periodic as well, like in case of a timer. But many a times they could also be an aperiodic events, such as arrival of messages over a communication bus. And when they would arrive, nobody knows. So they are stochastic in nature. So they can arrive at unknown points in time. So that is what an event triggered system is, really. So why do we really need to work with time triggered systems? So time triggered approaches provide an effective foundation for a reliable real-time system, because during the development and after you have actually constructed it, it is easy to model the system as compared to an equivalent event triggered design, and thereby determine whether all the key timing requirements have been met. This can help reduce both the test costs and business risk. What I mean by that is, when you have an event triggered system, as we saw just in the previous slide, these events could be external events and they are extremely unpredictable. The event could occur anytime and the interrupt is generated at any given point of time. So you really don't know how the system is behaving at different points in time. But when we have a time triggered system, you being the designer, you exactly know when a particular task is going to be triggered, because you have modeled that system. Since you know when a particular task is going to be triggered, it's actually easy to model the system, and you exactly know the entire timing of that particular system. That is, you know whether all the key timing requirements have been met by the system, because you know at every given point of time what the system is doing. So the system becomes predictable because you are using time as the decisive factor over here. And you know, at 1 millisecond, the system should be doing this. At 3 milliseconds, the system should be doing this. At 6 milliseconds, the system should be doing this. It is all known to you. So there is no uncertainty in the system. And because of that, testing the system becomes easier. And since you can test the system thoroughly, because you know exactly how your system is going to behave today, tomorrow, 5 years down the line. But the same cannot be said in terms of event triggered systems. Event triggered systems, you cannot model the system behavior at all. The reason for that is it is purely based on external events. So you don't know, you cannot simulate or understand all those events or test for all those events in the lab. But with TT, you can really know what your system is doing today, and whatever it does today, it's certainly going to do it the same way throughout its lifetime. So this can reduce the cost, the test costs and business risk, because as I said, it becomes more reliable. So naturally, it's not the warranty related issues and testing related issues, the costing that goes into it is greatly controlled. So that is one big advantage of such time triggered systems. So to say it or to summarize it, the time triggered systems are deterministic in behavior, and they offer some great advantages during runtime, because you know exactly what a system would be doing at a given point in time, and we can quickly determine whether the system is doing something wrong. Because if at all you know that every 5 milliseconds a particular task is to run, and if that task doesn't run, you can immediately know that something has gone wrong with the system. So that is how you would be really able to that is how you would be able to model your system right on the design board, and you can correct uh, all that went wrong during that entire test run of the system, because you know whatever that is going to do now, that is what it's going to do tomorrow, day after tomorrow, or maybe for the lifetime of that product. So this determinism is the key to making things reliable. And that is a general, in life also, anything that is deterministic, you know for certain that some things are going to happen. You are well prepared for it. But anything that is not deterministic, that could be a biggest hurdle, or it could be a source of uncertainty and fear. So it is always better to be certain about many things, uh, uh, or certain about most of the things in systems that you really make. So what does a time triggered system offer us? So summarily, TT approaches allow us to model the system behavior precisely as I said. Then during the development process, we can demonstrate that all the system requirements have been met. That means you can test it. Your test cases that you would be making, you have all your test cases ready, because you know how the system is going to behave over the entire period of time. So you can test it for all the known cases. But in event triggered systems, you cannot say for sure that you know all the test cases, because there could be some kind of permutations and combinations that may arise at some point of time during the system operation. So in time triggered systems, we can demonstrate this right during the development process. That is how it is. And when the system is running, you can detect problems quickly, because you know how the system is going to behave over the period of time. So if there is some kind of a behavior that you really did not expect, you can immediately spot it when you're testing it and testing it during the runtime. So this makes your system extremely reliable over the period of time. And this is why time triggered systems are used in safety critical domains that we saw earlier, like automotive or aerospace or industrial, or for that matter, rail. So all these places you can, where reliability of the system is essential because it directly deals with the life and death scenario, it really becomes important. And many of these systems, when it comes to aerospace, the costing involved is extremely high. So you have to pay both in terms of life and in terms of money. So you have to ensure that your systems are reliable and safe. That is why time triggered approaches are widely used in such systems as opposed to event triggered approaches. So this approach, that is the time triggered approach, gives us a high level of confidence in the system. That confidence tells us that the system is going to operate precisely as required. It will move into an appropriate state if a problem occurs. So the system should really put itself into that state if it detects some kind of a problem during its operation. So the system should put itself in a state that, and we call it the appropriate state, so that the loss or the damage that occurs is minimal. And this is you can see say the fundamental the seed of functional safety. That is, the system is functionally safe and it will minimize loss. So that was just a brief idea about what these systems really are, and what is a time triggered system, why we need it as opposed to an event triggered system, and what are the sectors in which you could really use these kinds of systems. So that is that deals with safety and reliability of the systems. So now we will see a little bit more about, as I said, I had spoken about Misra C, and now we will see why we are really focusing on the C language when it comes to these kinds of systems. So it's C that is the norm over here. You have to use the C programming language, and there is really no replacement for C programming language. It's C is really essential for such kind of system. So we'll have a look at it now. Let me just share my screen with you. Let it go. Okay. I hope the screen is visible. Ms. Rasi?
Yes,
Yeah.
sir.
Yes, sir.
Yeah, great. So now we are going to see this because these are the building blocks. You should be aware of these things before you dive into time triggered systems. So this is a glimpse into the general coding standard. So how you have to write your C programs. Why focus on this coding standard is what we are really going to see. Okay. So the C programming language is growing in importance and use for real-time embedded system applications within the automotive industry. I have heard these discussions, and there are numerous threads on the internet where some people say that C is dead and C is not really relevant in today's context. But these assumptions or these views of such people, they are really, I would say, they are naive for a simple reason. C is one of those languages that has sustained or passed the test of time. There is no language in the world that is as old as C that is being widely used. And since it has been around for almost, I would say around 50 years now, it is well understood, it is well documented, and people are now aware of all the nitty-gritties and some of those unpleasant aspects of C. So that itself makes it even more relevant for safety critical systems, because when you have data about a particular thing, lot of data, you can really make informed decisions. And if you see, Python is written in C. So C is the base of everything. It's only, every language has got its own pros and cons. Even C has them. C has its pros and cons, but there is no language that is like C. So C language is growing in importance for use in real-time embedded applications within the automotive industry. And with these electric vehicles and autonomous vehicles, when it comes to firmware development, C is the natural choice. So I would greatly advise all the participants over here to really learn C and believe that when you learn C, you have actually learned a language that is in the mid level. It is neither a high level language, neither a low level language. We will come to that slightly later in this particular segment itself. But it is the most fundamental and the most essential language that you really have to learn. I don't know whether today engineering colleges are really teaching C as one of the beginning languages. I think they have shifted over to Python just for the because Python is easier as compared to C when it comes to its usage. But if you really want to make it big in the industry, I would say you should know C. And just not know it, you should know how to write C. Knowing the language and knowing how to write, there is a huge difference. We'll come to it. So this, as I said, C is really growing in importance, and it is around for almost 50 years now. And why is it growing in importance? This is because it is inherently flexible. And the extent of support and its ability to port across a wide range of hardware. See, it is one language that can be easily ported across different hardware that is available. And the reasons for such kind of flexibility is, number one, many of the microprocessors that we use, if there is any other language available besides assembly language, then it is usually C. Have you heard anybody writing some kind of a program for a microprocessor in Python? Nobody does that. Or for that matter, in Java, nobody does that. It is only, apart from assembly, it's only C. And in many cases, other languages are simply not available for the hardware. So in some of the languages, you cannot use on a particular hardware. Those are the constraints of those languages. But C is a universal language, will run on almost any platform. C gives us good support for high-speed, low-level input-output operations, which are essential to many automotive embedded systems. I'm just focusing on the automotive sector because I feel this particular sector is the next big sunrise sector all over the world, because it is the only sector that is undergoing a major change. For till now, automobiles were viewed as ICE engines, internal combustion engines, which was more into that mechanical zone. But now vehicles, no matter what kind of a vehicle it could be a two-wheeler, it could be a cycle, it could be a four-wheeler, it could be a truck for that matter, or it could be a bus. Everybody is moving towards electric vehicles, and the Indian government has already said, I mean, it's going to be electric 2030. And now you can see the explosive growth of electric vehicles here in India, and Indian manufacturers have made a big impact in it, especially Tata Motors with the new vehicle that they have. So it's electric everywhere. Apart from that, you need great amount of charging stations which have to be reliable. So all these are, in a sense, going to create a massive requirement of trained, skilled manpower in this domain. So it's good that you learn these techniques and make yourself ready for the next big jobs in the market. It's only time, it's just because of the pandemic that we have been set behind by some time now. But otherwise, we were right on track, and things would be really looking great in that direction. But it's just time now. Ultimately, it will happen. So you should be really ready for that. Increased complexity of applications makes the use of high-level languages more appropriate than assembly language. Now, this is one point of contention. Today, it's really not essential that you write your programs, the firmware in assembly. You can write it in C because the compilers that are available are extremely efficient. So the kind of the performance that you may get some good compilers. I'm not talking about any compiler. So the kind of performance that you can get out of these compilers is equivalent to what you can get through an assembly language. So rather than writing it in assembly, it makes sense to write it in C, and that is what is preferred nowadays. So you should focus more on C, and since the applications are becoming more and more complex, you need to have a language that is above the assembly language. So the right choice is C, which is a mid-level language. And C generates smaller and less RAM intensive code than many other high level languages, because it is the code that it generates, the compilers that generate the object code, the object code is very, very compact. So with limited constrained devices, when I mean by constrained devices, I'm talking about microcontrollers that have very little RAM in the order of KBs, or a few about a 1 MB or 2 MB. Some of them have that kind of RAM. C is the perfect choice to actually write your code, because you can write good amount of code. In fact, you can create an entire system using C, and not worry about the RAM requirements. You don't even need, many a times you don't even need external RAM, because nowadays these microcontrollers are having good amount of RAM internally that can support most of your applications. So C can generate smaller and less RAM intensive code than many other high level languages. And a growth in portability requirements caused by competitive pressures to reduce hardware costs by porting software to new and lower cost processors at any stage in the project lifecycle. So what I mean by this is, today it's more of competition. There are companies that are making similar products. So portability is the key. So now it also boils down to how you write code that is generic and can be easily ported from one family of microcontroller to another. That is, say you have written code for 8051, and now the code should be written in first place in such a way that you should be able to port it easily, say, to an ARM architecture. And you will not actually change the main logic of the program. You just have to change the basic architectural related design aspects of that code. That is, whatever that is specific to 8051, only that needs to be changed to fit into an ARM Cortex derivative. So this is only possible because of C. So it can be easily ported to a different lower cost processor, and you can make a multitude of similar products on different platforms. That will allow a company to really, really make huge profits and create, different kinds of products which are similar but have different platforms. So that is very essential. C gives you that flexibility. Now with that flexibility and that great these, you can say, these are some of the big aspects of C programming. But then also that C language has got some insecurities inherently built in it. That means nothing is perfect in this world. So no programming language in this world can guarantee that a final executable code, that is the object code that is created when you actually compile your code, will behave exactly as the programmer intended. It could happen because of some programmer mistakes or inherent problems within the language itself. So there are a number of problems that can arise with any language, and these are broadly categorized below. Examples are given to illustrate some of the insecurities in the C language. So let's go through it a little bit in detail. The first and foremost is the programmer is making a mistake. The programming language has a bearing on this type of error due to the following reasons. Now, a programmer could make a mistake either by his own virtue or because of some parts of the language itself. It's not that the programmer made it. It's because either there could be some parts in the language that could cause this kind of confusion. So what is it? What are the reasons that the programming language has a bearing on this type of an error due to the following reasons? So firstly, the style and the expressiveness of the language can assist or hinder the programmer in thinking clearly about the algorithm. So how the language allows you to express your ideas, that itself can be a biggest hindrance for the programmer to think clearly about the algorithm that he's trying to make. Sometimes what the programmer can create an algorithm, but because of the expressiveness of the language, it becomes more cryptic to write it. So C language allows us to write well laid out and structured code, but at the same time, it also allows us to write perverse and hard to understand code. That means, see, it's like, the classic example would be a person who is really good at writing multiple redirections using pointers. Say about 2 or 3 levels of redirection. When it goes beyond that, it really becomes difficult to really visualize what's happening in the code. But some people are really good at that. And another person who really doesn't understand it may misinterpret the code. And then all sorts of problems will start arising. So that is what I mean by, write perverse and hard to understand code. So it is inherently in C because of its the way the language is, especially when it comes to pointers. So pointers are not, I would not say that pointers is causing the problem. The problem is how it allows, I mean, how pointers are expressed. Some people don't understand it. Some people really understand it well. So that can cause some kind of a misunderstanding. Then the second problem when it comes to programmer mistakes, the person who's writing the program. Secondly, the language can make it easy or hard for typing mistakes to turn one valid construct into another valid, but unintended construct. That means the programmer is trying to write something, but just because of neglect or oversight, it could convert his statement into something else other than what he or she had planned to write. Thirdly, the language may or may not detect errors when they are made. So you may not have a way to really detect these errors as you are writing them, writing the code. So syntax of C is such that it is relatively easy to make typing mistakes that can lead to a perfectly valid code. That means you have written some syntax, but that can really change the logical flow of that particular program. And these are some typing mistakes, but it is a perfectly valid statement. So for example, it is all easy to write a single equal to, that is an assignment, instead of a double equal to, that is a logical comparison. And the result is nearly always valid but wrong. That means you're getting a result, but you are not expecting the one is the assignment, one is a comparison. So the results would be produced, but this is not a correct result that you want. So it is a wrong result. So this is inherently there in the programming language. So programmer can make mistakes while writing it. Thirdly, the language may or may not detect errors when they are made. The philosophy of C is to assume that the programmers know what they are doing. That means, see, this language doesn't tell you or point out some of the mistakes that you would make while writing it. Because C assumes that the programmer knows what exactly the programmer is trying to write, which can mean that if errors are made, they are allowed to pass unnoticed by the language. So there is no inherent language checking over there in C. An area in which C is particularly weak in respect of type checking. C will not object, for example, if the programmer tries to store a floating point number in an integer that they are using to represent a true or false value. So most such mismatches are simply forced to become compatible. So it's not going to complain, but it could be a big potential source of error. So it is not. You can say it's weak with respect to type checking. So that is the third aspect. Now that was these were some of the aspects, when it comes to a programmer making a mistake. Now the second big aspect was the programmer himself has misunderstood the language. What does that mean? Programmers can misunderstand the effect of constructs in a language. Some languages are open to such misunderstandings than others. That means some constructs the programmer has totally misinterpreted. And it's very common. We see it happen time and again. Because today people use a number of languages, and it is very common, to when you are actually coding live, to mix up certain things that from the other languages, and you just go on writing the code. Logically, the code is perfect, but when it comes to the nuances of the language, it can cause real problems. So there are quite a number of areas of C language that are easily misunderstood by programmers. An example is the set of rules for operator precedence. This is very important, though very many people just skim over the operator precedence. These rules are well defined in C, absolutely well defined, but they are very complicated, and it is easy to make the wrong assumptions about the precedence that the operators will take in a particular expression. Many a times we have seen, when there are a lot of expressions that you are going to have in your code, it's just that the precedence of the operators causes a lot of problems. And these are not really understood by many programmers. The reason for that is the rules are absolutely clear, but they are slightly complicated to really implement. We have seen that. Then the third most important aspect of insecurity in the C language is the compiler doesn't do what the programmer expects. So if a language has features that are not completely defined or are ambiguous, okay, that means inherently there is something that in the language that is not completely defined. Completely defined in the sense you really don't understand what it would do, because there is ambiguity. It's not very clear. See, it's like, if I say you can come tomorrow, I have defined it. You come tomorrow, but it's not very clear. It's not completely defined. I have not told you at what time you have to come, where you have to come. If I tell you, you come tomorrow at 10 a.m. at SPIT, it is completely defined. But if I say you can come tomorrow, it's open. I can come tomorrow at any point of time within the 24 hours of that date. So this is what I mean by completeness. So they are not completely defined or are ambiguous, and the programmer can assume one thing about the meaning of a construct. It's now left to your imagination or your own interpretation. But the compiler will interpret it differently. The interpretation of the compiler is different, and the interpretation of the programmer is different. And this can cause a mismatch and cause all sorts of errors. So there are many areas of C language which are not completely defined, and so behavior may vary from one compiler to another. The reason for that is how the compiler is created or implemented. And the fourth potential source of problem is the compiler itself contains errors. See, no software in this world is perfect. No matter what care you take, what kind of testing you do, there is something or the other, some residual bugs that are left within that software. And the same applies to compilers as well. The compiler itself has got errors. A language compiler and associated linker and the associated other things that come with that, probably the integrated development environment that you're using. That means the entire software tool that I'm talking about. So compilers may not always compile code correctly. They may, for example, not comply with the language standard in certain situations, or they may simply contain bugs, because the creators of those compilers have themselves not understood the language nuances very clearly. So this could also be a potential source of an error. So because there are aspects of C language that are hard to understand, compiler writers have been known to misinterpret the standard and implement it incorrectly. So this is very common. Everybody has got their own interpretations of the compiler, and that can cause a lot of different kinds of errors that can crop up in your own programs. Okay. And then finally, the most dreaded runtime errors. So these are the errors that you will only catch when you are running the program. So a somewhat different language issue arises with a code that has compiled correctly, but for reasons of a particular data supplied to it causes errors in the running of the code. So languages can build runtime checks into the executable code to detect many such errors and take appropriate action. So what it means is, whenever you have written some kind of a statement and you have provided some kind of a data, and that data, the way it is processed while the code is running, that can produce results that you didn't expect. So what you need is you need some runtime checks into that executable code to detect such errors and take appropriate action. That means if an error is generated, you really need to take some action if some kind of an error is generated. And C is generally poor in providing, that runtime checking. That runtime checking is not there. So this is one of the reasons why the code generated by C tends to be small and efficient. Now you are paying the price of runtime checking, but on the other hand, you are gaining something extremely essential: efficiency and size. Now, that is what I said. You gain some, you lose some. Now, when it comes to such constrained devices meaning where there is little RAM, what is essential is you should be able to have code that is extremely small, executable code, that is the object code, and it runs efficiently. So you are paying a price over here. You are losing that runtime checking because C is very poor at that. So, but there is a price to pay in terms of detecting errors during execution. So C compilers generally do not provide runtime checking for such common problems as arithmetic expressions, example divide by zero, overflow, or validity of addresses for pointers or array bound errors. They crop up if you try to access some array indexes that are out of bounds, and they generally come up during runtime. So there is no way in which you can check it at during design time. These can come up during runtime as well. So from all these things that you saw, these 5 points that we discussed, it is clear that great care has to be exercised when using C within safety related systems. Now comes the big question. You saw these different issues or language insecurities as we were talking about. Why we were talking about this? These are the different sources of potential problems while you're designing your system or writing your software. So some of them are inherent, some of them are created by the designer, some of them are a part of the tool that you're using, and of course the compiler. So many a times you don't have control on certain aspects of this as a designer. You can't change the language standards. You can't change the compiler the way it is written, because these are coming from various sources. So it should be now clear that considering these 5 points that we just saw, we need to take great care when using C with safety related systems. But trust me, there is nothing better than C for creating such kind of systems. Because of the kinds of issues identified above, various concerns have been expressed about the use of C on safety related systems. Imagine you are a brilliant designer, a brilliant programmer, but because of some basic inherent problems within the language itself, you are faced, or you have designed an aviation system, a part of the entire aircraft design, which fails while the aircraft is airborne, and you have created the best of the design which cannot fail, and you have tested it in your tests that you have conducted in the lab, and still a problem has arisen. Now who is to pay the price? You as a designer or the creators of the language itself? So you have the responsibility has to be fixed on somebody because lives have been lost. You must be aware of what happened with the Boeing Max. It was grounded for almost 1.5 years because there were 3 crashes, and Boeing was made to really give answers for the failure. Now there were these were software errors that were there in their design. Basically, that is what was being widely circulated in the media. And now I think they have got the permission to actually make the aircraft airborne after reviewing the safety related issues of that aircraft. So, because of the kinds of issues identified above, various concerns have been expressed about the use of C on safety related systems. Certainly, it is clear that full C language should not be used for programming safety related systems. That means, as I said, there are some language insecurities which you really have to take care of, and you should avoid using those parts of C that can cause some real safety related issues in your design. So, however, in its favor as a language is the fact that C is a very mature and consequently well analyzed and tried in practice. See, there is no language in the world that is used so much as C is used. With the amount of data related to C's usage, the type of algorithms that C has been used to make, it's well analyzed. Therefore, most of the deficiencies of C are extremely well known and are in the public domain, and they are understood very clearly. So there is also, and one big advantage that you have is there is a huge tool support available commercially. There are some best tools in the world that you can use to create your firmware designs, like Keel tools from ARM. They are, I would say they are the de facto standard for development of such systems. We would say that some of these compilers are, their tools are really great. So therefore, why is it possible? Because with the amount of data that is available, all these creators of these tools, they know the problems associated with the language, and all that has been taken care of when these compilers are made and these tools are made. Because these deficiencies are extremely well known, because C has been around for so many years. Therefore, its deficiencies are known and understood. There is a large amount of tool support available commercially, which can be used to statically check the C code and warn the developer of the presence of many of the problematic aspects of the language. So there are some tools from different vendors that allow you to really check whether your code that you have written adheres to certain standards. So it actually wants the developer during when the developer is actually writing the code about the presence of some of the problematic aspects of the language that the programmer might be using unknowingly. So that right from the development stage of the program, care is taken. That is what is essential. So if for practical reasons it is necessary to use C on safety related systems, then the use of the language must be constrained to avoid as far as is practicable those aspects of the language which do give rise to concerns. So basically what we are saying over here is we are going to use C, that's for certain, in spite of all the language insecurities and the problems that we saw, because there is nothing better than C available as of now or in development anywhere in any part of the world that you can use in place of C. So how do we go around this? Then do what? Use a constrained part of C. That means avoid those aspects of the language that can give rise to concerns. Don't use those parts of the language. So you create a subset of that language. So this document that you make, or you're going to use a ready-made document, which provides a set of constraints. That means the constraints are defined. Don't do this, do this. Do only this much part of the language. It is referred to as a language subset. So we are not going to use the entire C. We are going to use a subset of it. This language subset is called the MISRA C. It is a coding standard. So basically, what is this MISRA C? There are around 21 rules with sub-rules under each rule in this standard, against which developed code can be checked for compliance using commercial tools like the LDRA toolsuit. This is one of the toolsuit name that we have used over here. It's not that we are promoting this tool set. It's just that it's one of the tools that people can use, to figure out whether the code matches a certain standard. So C lays down some rules, and you have to design your code following those rules so that your code automatically complies to the norms set in within MISRA C. You don't need to really think about whether your code is compliant or not. If you follow the MISRA C coding standard, your code will automatically comply with the safety standards that are needed. So that is how we have arrived at the subset. And this actually originated in the automotive sector, and now it's widely used in different sectors. It was created by a consortium of the automotive giants. So we will just show some 5 rules. There are different rules over there. I will just show some 5 rules just for illustration purpose, what it really means to have a MISRA C standard in place. So just a minute, let me just open up some document. Just give me a moment if I can show it to you. Yeah. So I'll just share the screen with you now. I hope you can see this screen over here. It's a Word document. Is it visible?
Yes, sir.
Yeah. Yes, sir. So I'm just going to show you some rules, that MISRA C says you should follow. And there are some extremely basic rules as well. You would be surprised to see that. It's all, that means that shows the amount of detail that it goes to. The first and the most simplest rule. It says that it's a rule 2.2. It says that source code shall use only / star / style comments. This is a commenting style, right? All of you know we comment our statements using this. I've highlighted it over there. So what it means is, it means that the comments in the code should be encapsulated in between / star and */. Use of double forward slashes for commenting should be avoided. So what the standard says is, don't use this style of commenting. Use this style of commenting. And why is it so? This type of commenting may provide for uniformity and consistency in using comments in the code. Of course, this interpretation we have done. It's not the coding standard just tells you what you should do, what you should not. And these parts of the code are not compiled. So valid C code which breaks this rule. Now this code that you see is a perfectly valid code, right? But it's breaking the C MISRA C standard.
Sir, can you zoom a bit?
A little bit. Yeah. Is it okay?
Yeah, thank you so much.
Yeah. So if you see that this part of code over here, it's a perfectly valid C code. There is no issue with it. But if you are to follow a MISRA-C standard and you document it and say my code is MISRA-C compliant, and a tool checker finds out this statement, it's going to reject your code right away, saying that it does not comply with MISRA-C coding standards. The reason for that is you have used double forward slashes. So this is one of the rule. The other rule is the character sequence /* shall not be used within a comment. Now see, this is just dealing with, comments. So imagine the depth of this this rule set. It means that the comments in the code should not be nested. Any comment should be encapsulated like this. If we do this, see, if we do something like this, if you write this, the starting /* will actually close this //, but it can cause undesired behavior. And this is a type of an error that can cause inadvertent commenting of code accidentally. What that means is, if you see this code over here, it's the commenting starts here. If a is 10, this is just a statement that I have written, and then I write my C code if a is equal to 10, and then I write this show the value of a as a comment over here, and then I write printf. This is a valid C code, but it always prints the value of a instead of printing the value of a if a is 10. You're getting this? The reason for that is the style of commenting, and this can happen, when a programmer is really testing out during the design phase, and he forgets to remove the comments. So never do such kind of commenting in your code, and the tool checker will immediately catch this. There is no error over here, but the way the results are interpreted, they can have catastrophic effects on the final outcomes of the running system. So that's rule 2.3. Then there is another rule that is in 2.4. It says sections of code should not be commented out. That means we have this tendency many a times, we do this while we are writing our code. We start off with let's say we have assumed that we have a variable a 9 is assigned to that variable. And then we put this in comment. Okay. Now we don't want this to work, because we want that a to be 9. Now instead of doing this, use conditional compilation. This is not the right way of doing it. Use conditional compilation. That is, use this if def, if not def kind of constructs. So this is what you should really take care of if you want to make your code compliant with coding standards, and you want to make your code really safe for such critical systems, you have to follow this. So if at all I had to write an equivalent of this using conditional compilation, I could have written like this: hash define a10, if a is defined, printf a, else printf number is not 10, and end if. So this is the conditional compilation, the equivalent of this. Use this kind of coding statement. Then there is one more rule which deals with trigraphs. Now trigraphs are not really relevant in today's world. Trigraphs are actually relevant in legacy systems, that is older systems which had constrained keyboards. So what it means is trigraphs begin with 2 question marks followed by another character. For example, question mark greater than means a curly bracket, a closing curly bracket, because all these these characters were not available on the keyboards in the earlier days. But there are many legacy systems that are still existing in the world. So if you have such kind of a code, your code will automatically be rejected by the tool checkers for not being compliant. So trigraphs are interpreted differently by compilers that are used today and can cause erroneous results. So valid C code that breaks the rule. This is a valid C code. You can see there is no problem with that code. But the above code can be erroneously interpreted by a compiler as a curly bracket, when the meaning of that thing was not a curly bracket. The programmer really wanted it to be like question mark greater than. Then there is one rule 5.1. There are many rules. We have just picked up some of them to just show you some nuances of the language. Identifiers, internal and external, shall not rely on the significance of more than 31 characters. So what it means really is, means that the identifiers must have distinct first 31 characters. Even older compilers will be able to distinguish between characters. So valid C code, which breaks this rule. If you see, I have this identifier, and then I create another one that is exactly identical. It only differs in the last character. In the above code, both the identifiers are same, since they are identical in the first 31 characters, although the 32nd character in the second identifier is different. So if you try to create something like this, it's certainly going to be a flag would be raised that the code is not MISRA-C compliant. So there are many such rules over there. This is one with the identifiers in the inner scope shall not use the same name as the identifier in the outer scope, and therefore hide that identifier. Many a times we have this tendency. See, we have one integer as a, and then within the scope of this while we have again redefined it. This is at file level. This is at block level. The one that I've highlighted. This is at file level. So it says that identifiers in inner scope shall not use the same name as an identifier in the outer scope, and therefore hide that identifier. This is not permitted. You can't do this if your code has to match the standard. So we have just shown some of the rules for illustration purpose, what MISRA-C coding standard really tells you about, what it really means, and why you should really have code that's going to really match the standard, and what are the advantages of really making such kind of a code basically. So you have seen now how a coding standard can be used to an advantage and make your system compliant with certain international standards, so that you can sell your products in the international market. Otherwise, just writing code and making some amazing product without having all these things in place, you cannot be successful in this domain. These are the most important aspects of system design when it comes to firmware design of such systems. So if you're going to write some embedded code, all these things become extremely, extremely important. So what we have seen effectively is till now is what is the idea of a time triggered system? What is the basic idea? We will see the implementation now. We have seen what is the basic idea of a time triggered system. We have understood why when we are talking about safety critical domains where life and death scenarios are involved of humans, and most of these systems are in that zone. Because if you see an aircraft, if you see a car today, it's made up of numerous embedded systems, or you can say embedded modules, which are communicating with each other to make that entire system work. So you have to ensure that all these systems or subsystems that you have or modules that you have are extremely safe. And how to ensure that? First of all, you should have a great architecture that gives you the ability to predict the system behavior, know exactly the system state, and most importantly, at runtime, the system should be able to detect any kind of a failure and try to force the system into a fail-safe zone. And a language that will assist you in creating such systems, and how to take care of the inherent insecurities of the language that exist in that language. So all that we have seen so far. And if you have any questions, anybody can just put a question. If anybody has anything to ask, you can certainly ask before we move on. Nothing? Okay.
No,
Sir,
Govind sir, there's a question in the chat box.
1 minute. Actually,
Shall I read?
1 minute, sir.
I'll read. Is the
Yeah.
concept of pointer necessary for time trigger architectures?
Okay, that was a great question. See, as far as possible, in time triggered architectures, we avoid the use of pointers. We have avoided the use of pointers for a simple reason, because many a times it really becomes difficult to maintain such systems, and maintainability of the system is very key. So very rarely you will see the use of a pointer, and which makes really the readability of the system difficult. I hope that answers your question. Anything else? Okay.
How
We are going to,
how the watchdog timer is different than time triggered architecture?
okay.
From Mr. Ravi.
That's a great question. We will actually be addressing a little part of this in the tutorial in the later part. But we are not going to go into the details of the watchdog timer. But yes, the watchdog timer plays a big role in time triggered architectures to make the system safe.
Okay, done. Any other questions? Okay.
Do we use
Leena madam is asking, do we use interrupt timers to generate internal timers to generate interrupts in time trigger?
Okay. Actually, the thing is, we are using some specific timers that are generally meant for the exclusive use of interrupts. That we are actually going to use a single interrupt concept. But yes, many a times you cannot just work with single interrupt. But when used with more than one interrupt, you have to be extra cautious about how you're designing the system. But many a times it would be a single interrupt concept, and the timer that we are going to use is an exclusive timer. In most of the architectures, you have an exclusive timer that is going to generate a system tick. We generally avoid using general purpose timers when you want to generate a system tick. Like in case of ARM derivatives, you can use a SysTick timer, which is present on all ARM derivatives manufactured by different manufacturers. And in case of 8051, there is one specific timer, that is the timer 2. We will see this in the seminar after we begin with the next thing in the next 10-15 minutes. So that time we will see what timer we are using. So in 8051, we are going to use the timer 2. And if you are on the ARM derivatives, the best timer to use for generating system ticks is the SysTick timer. That is the internal timer, which is exclusively designed for such kind of things. Yeah.
Yeah. Okay, sir, you can go ahead.
Yeah. So I think, sir, shall we have a break of 10 minutes?
Yeah, it is up to you.
We'll be back at 11:30.
Okay, so participants will be back at 11:30. I'm sure sir has announced that there is going to be a quiz also.
Yeah.
And those who are interested in having the what sir is providing, or Micro Device and Safety Systems is providing those facilities like their training programs and the boards, you should hear the session very carefully and then attempt that quiz. So that quiz will be around 12:30 or so. So please attempt that. And second quiz also in the afternoon. Dr. Pond will be joining us at 2 o'clock. So he will be with us from 2 to 3. And then you can also ask the questions to him around 3 o'clock. And then we will have second quiz at the end of the afternoon session. And these two quizzes is going to decide the first top 20 winners who are going to get what sir might have already announced at the start of the session. Okay, so thank you very much. 10 minutes break.
Yeah, we'll be back exactly sharp at 11:30. It's
Sir,
11:20. It's 11:24.
राठौड़ सर,
Yes, sir.
वो वीडियो था ना माइक्रो डिवाइसेस का वो रन कर.
We would be using Google Forms.
नहीं, मेरे पास नहीं है वीडियो.
Should I play, sir?
Yes,
Yes.
yes, madam.
Madam, I think you're not shared with sound.
Okay.
Anyway, it's a break time. Huh? Participants, you can have this video will keep on running. You can stop and replay again.
राठौड़ सर, मैं मेरा कैमरे का कुछ इशू है, मैं रिस्टार्ट करके वापस ज्वाइन कर.
राठोड सर.
बोला साहेब.
सर या PPTs ते शेअर होतील ना?
सरांना विचारा.
ओके.
But in afternoon session, what Dr. Pont is going to say, that definitely we will share, sir.
ओके ओके.
Because I asked him and he allowed.
ओके, फाईन फाईन.
Yeah.
थँक्यू सर.
Okay, sir.
Sir, you are able to hear the sound now?
Yes, madam. It was very clear.
Okay.
Welcome back. Are we good to go?
Yes, sir.
So I hope you can see my screen.
Sir, your audio is too less.
Is it fine now, sir?
Now it is fine.
Oh, I had forgotten to put on my headphones. Okay. So, is my screen visible?
Not yet, sir.
Is it fine now?
Yeah.
Yes, sir.
Okay. So let's start off. So we are going to start off with a very fundamental things, and then we will proceed because we have to cater to different kinds of audiences, right from students to people in the industry and academics. So now, what is an embedded system basically? An embedded system is an application that contains at least one programmable computer, typically in the form of a microcontroller or a microprocessor or a digital signal processor chip, and which is used by individuals who are in the main unaware that the system is computer based. So basically, an embedded system is nothing but it should at least have one programmable computer. Now that computer could be in the form of a microcontroller, a microprocessor, or a DSP chip. And it is a system that would generally be used by individuals who may not even be aware that they are actually using a system that is computer based. Like if I have to really put it in crude words, if at all there is a truck that a truck driver is driving, that truck may have at least about say 50 or say 80 different microcontrollers at work in it, and the truck driver has nothing to do with it. Those different microcontrollers may be controlling the different aspects of the truck, and truck driver is just going to use the truck without even being aware of the fact that he's actually using a computer based system. And today's vehicles, they have become extremely uh, electronic based, and with the electric vehicles around, it's almost going to be a totally a different ball game now. So that is what we generally mean by an embedded system. So these are some of the examples of the embedded systems. Many of these are on that borderline where we can say that it's an embedded system or a full-fledged system which does not classify to be called as an embedded system really in today's context. One of them that you really not call an embedded system in today's context is the mobile phone. If you see the mobile phones that we used some time ago before the advent of Android phones, some of you must have seen those phones or used those phones, like the Nokia phones that we had earlier. They were not customizable at all. You could not download anything into it, or you could not really change or customize the way the phone's screen looked. Nothing was customizable. That was a pure embedded system with the firmware built right into the chip. But with today's Android phones, you can customize your phones, you can download things, you can upload things. So it's more of, you cannot say that it's that kind of an embedded system that we are generally going to deal with. We are going to deal with deeply embedded systems, meaning embedded systems that whose firmware you cannot, the end user cannot change. Like say a washing machine, how the wash programs work, they are fixed. When you tap onto a key of that washing machine, it's going to do the same thing. You cannot reprogram the keys. So that's a deeply embedded system. A deeply embedded system is that in which the end user cannot customize the way the software works. So you can see the game, the gaming controller, the remote control, Then these small digital watches. I'm not talking about the intelligent watches here. The digital watches that you generally use from Casio, or for that matter, the set-top boxes, the camcorders. Then you can say the monitor screen. That is also an embedded system, because when you turn on the monitor without the signal, you would see the logos of the manufacturers like Dell or LG floating on the screen. All that comes from the firmware. So all these are examples of embedded systems, but not all of them are in the critical zone. Most of them are household appliances, is what you can see. So these are some of the examples of embedded systems. And with time, you know, some of the there is a thin line between an embedded system and a deeply embedded system. We are more interested in the deeply embedded system. So now, what are the metrics of an embedded system? So whenever you're planning to really make a product, what is important to consider are these points. What would be the performance? That is the throughput or the execution time of your design that you're going to make. Energy efficiency, which is the most critical aspect in today's world. You people are really looking at energy efficient devices. You would not require a system that needs constant charging. You want to make your system as energy efficient as possible, and this is also possible to make it energy efficient apart from the hardware aspects. You can make it energy efficient with the right design in software. Then the size of the embedded system, which is very critical in cases like a pacemaker, the physical constraints, the physical dimensions of the product. Then flexibility. Now, what does flexibility means? Flexibility means you have to have a design that is as flexible as possible, so that you can just, with little changes here and there, you can create a new product altogether, because this will directly affect the profitability of the company. If you have a great architecture that with slight tweaks can create an altogether a different product, and you can get that product in quick time into the market, that is very, very, very essential in today's world. The cost of the product, it has to be extremely competitive. Now that depends upon a lot of factors, like the hardware that you're using, the software that you have made, how you have made it, how many people were involved in it, what kind of architecture you're using. That also defines the cost of the product. Then one of the other aspects, which should not be neglected under any circumstances, if you really want to sustain into the market and really make a killing out of the product that you have made, that is the non-recurring cost. That is research and development. It's extremely important that good amount of R&D facilities are there, so that you can really create newer products with some basic changes in the architecture. So this is a non-recurring cost. It's not going to recur again and again, because once you have an R&D in place, you're not going to play around with it. And finally, it's the time to market. Now, this time to market is governed by, the flexibility and the research and development. So if your architecture is flexible, you can reuse it and really make a new product out of the existing architecture in quick time. And that is possible if you have a great R&D, research and development team and a research and development department right in your team, so that whatever products you make are quickly marketable, so that you can put them in quick time in the market, which directly affects the company timelines. So when it comes to embedded system design, these are the points or metrics that you should really take into account when you are really making such kind of systems. Now, when we are talking about the energy efficiency, many of you know today there is a huge talk of green earth and saving energy, making devices work on natural resources as far as possible, if it's possible. So all it is an entire approach. It's an approach of the hardware selection. It is the approach of the correct software design. And there are a lot of things that you can do in software to make your system energy efficient. This plays a big role. So all these things, if you take into consideration, you should be able to really make a product that will really stand out and be saleable across the world. See, today, if you, since our economy has opened up, there are international players in our country. You should be able to match up to their performance, and you should be able to adopt the methodologies that they have been using to actually make these things really happen in reality. So now, as I spoke earlier, what is reliability? Now we come to the technical understanding of reliability. The ability of a system or a component to perform its required functions under stated conditions for a specified period of time is reliability. That means if I have a system and it's doing, say, it's designed to do only two things. It's designed to do only two things, two functions. Those two functions, that system should be able to perform under the conditions that it has been said that they would perform those two functions under those conditions for, say, 365 days. Then the system should keep performing those functions, those two functions, under the given conditions for 365 days without a break. If a system is able to achieve this feat, then I can say that the system is reliable. But if it fails even on one count, then the system is not reliable. So this is very important. It's the ability of the system or a component to perform its required functions under stated conditions for a specified period of time. That means reliability. So reliable embedded systems, there are different aspects to it. We are going to focus on the function on the software aspects of it. That is functional correctness of the software that you have made. You should be able to verify and prove that that this software will correctly function under those stated conditions. We should be able to prove that the system would enter the proper state if at all there is a failure detected by the system. That's functional safety. We should be able to prove that it will perform those conditions, those functions under the stated conditions for a given period of time. And we should be also able to prove that a system is going to be stable. And most importantly, we should be able to prove that whatever tasks are to be executed, they would be executed at the right time. So the timelines also have to be proved, which is very important because that is the essence of time triggered architectures. It's time, time, and time. So the timelines have to be met. Apart from that, all the other factors like the functional correctness, the functional verification, the functional safety, the reliability, and the stability of the system, all this together, put together, will make your system reliable and safe for operation. So reliable embedded systems, we will introduce a range of programming techniques that will help you create embedded systems which are reliable. And why do we need reliability? It's apparent that reliability is needed in places like you have, say, a pacemaker in somebody's body. You cannot have a system or a pacemaker that is working today, and after, say, about a year's work or about 5 years work, it fails. You don't have the liberty of just opening up the body every 5 years or every 2 years and getting the pacemaker replaced or repaired. This is human. This is human life. That would be ridiculous. if you are expected to do that. So reliability is the key in such scenarios. Reliability is the key when it comes to aircraft systems. All the airplanes that are flying, no matter what, commercial or fighter or cargo planes, they have to be reliable, because there are two aspects involved over here. One is the human aspect and one is the big cost aspect. Imagine a company making an airplane and the airplane is flying and suddenly it falls down. You cannot have a system that is so unreliable, and that would directly affect the existence of the company itself. More general embedded systems like household goods like the washing machine, or even for that matter your home-based players, the music players, or whatever kind of electronic equipment that you have, they also need to be reliable. You cannot sell a product to an end customer, because this is fast moving consumer goods. You cannot sell a washing machine or a mixer grinder or a microwave oven or a television to a consumer at a low cost and it fails within the warranty period itself. The reliability and the believability of the people on that on that brand will be lost, and soon the company will be out of business. So these people, I mean, people who make such kind of white goods, they are more concerned about their brand image, because they will quickly go out of business if their products start failing in quick time. And they are also bogged down by another problem, that is they need to get products in quick time in the market so that they remain competitive. So they need products which need reduced testing times and reduced warranty costs. So how you can reduce the testing times? You can reduce the testing times by having a system that is reliable and whose functional correctness and whose functional safety is known, and you know how your system is functioning at every given point of time. So if you know how your system is going to function at every given point of time, any upgrades that you make to the system will also match to the system timelines, because you know exactly what's happening at every given point of time in that system. So that is very essential in the white goods segment. Now, we have already seen why we need the C programming, but these are some of the other aspects of why we need to use C. There are good, well-proven compilers that are available for all the different kinds of bitages of the microcontrollers, right from 8-bit to 32-bit or even more today. A lot of stuff is available at dirt cheap cost, because there is huge competition between programmers, and C being the mainstay of the computing world. There is huge pool of talented professionals available, and because of that, the cost of hiring also goes down for a company. So if you have this is the demand supply kind of a scenario. There are a lot of people available who are very good. So you have to, if you have to really stay in that competitive market, you should be equally good. Then the books, the training courses, the code samples, that is the code repository on the internet, they are widely available. So you can really use the ideas or the repository, of course, with attribution, for making these things really useful. Then, as I said, overall, C may not be an ideal language for developing embedded systems, but it is a good choice. We saw that in the earlier half. And it is unlikely that a perfect language will ever be created. So with whatever resources that you have for developing things, C is the perfect choice, but nothing is ideal over here. So why we use C? It is a mid-level language with high-level features such as support for functions and modules, and low-level features such as good access to hardware via pointers. So these are, hence it's called a mid-level language. We don't call C as a high-level language, though many of our literature and the books put C in that high-level zone. But if you see, technically, it's not a high-level language, because you can directly deal with the hardware through pointers. C is very efficient. We have seen that earlier. It is popular and well understood because it's been around for more than 50 years. And people who are well versed with desktop programming with, say, Java or C++ can very well understand the syntax of C easily. And as I said, extremely good compilers are available for all the different kinds of families, maybe 8-bit or 32-bit or 16-bit. So there is no a dearth of such kind of tools that could be available for you. So as I started earlier, we would be using 8051 as our target. But let me tell you, the time-triggered architectures that we are going to discuss, the choice of the platform is immaterial. It works on 8051. That same code would work on an ARM derivative. It could work on an AVR. It could work on a PIC. It could work on FPGAs as well. In fact, and even safety systems has created a soft core of, I mean, they have designed a soft core on the ARM architecture for porting this onto that soft core. Apart from that, it also can be ported to Intel Atom processor. In fact, it has been ported even to the branded Gigabyte Intel Atom motherboard. So it works everywhere. The reason for that is the architecture is universal. Architecture of this TT, the TT architecture that we are going to discuss, there is nothing that is dependent on the platform apart from, you know, wherever you need to use some specific registers of a particular hardware, there you have to make those changes. That's natural. There is nothing that is common across different hardware architectures. So those changes are bound to be there. But when it comes to the actual system design, everything else would remain the same. Only thing, the nitty-gritties are at the hardware level that you need to handle. Like, say, for example, we don't have the R0 to R15 registers in 8051, which are there in ARM. And if you're going to use something over there, you have to find an equivalent register here in 8051 and do those changes. So that goes without saying that those changes are bound to be there. But overall architecture would remain the same. So we are focusing on 8051 for a simple reason, so that most of the people know how to use an 8051. That's the reason we are targeting this. But otherwise, when we do our certification courses and we actually use these systems in the industry, most of them are ported to the ARM Cortex, either M0, M1, M0, M3, or M4, and for that matter, even the M7 that's come up. So there are different use cases over here. So we are going to focus on 8051. So most of you know that it has got 32 input-output lines. It has an internal memory of 256 bytes and internal program memory of 4 kilobytes. It has got 3 16-bit hardware timers and low power and idle modes. These are very important for us. And the different members of this family are suitable for everything from automotive to aerospace systems to TV remotes. And let me tell you one more thing over here. Let me add this, because even I have many people asking me, you know, how 8051 is relevant in today's world. If you see the market, and different semiconductor manufacturing giants, all of them, no matter whether it's an American giant or whether it's a European giant, or for that matter, there is a giant in the Southeast Asia, all of them still manufacture 8051 in different avatars. They have different flavors, but the core of it is 8051. So 8051 is not irrelevant. It is like the C programming language. It's old wine in new bottles. So it is, this particular architecture is the most elegant architecture and the most used even today. So don't be under the impression that 8051 is irrelevant. There is a lot of talk about all this on the internet, and many people talk about it. But our view is it's extremely relevant. The reason for that is you don't even take our words. I would tell you, to actually manufacture these chips, no matter how small or big the chip is, the amount of cost that goes into the manufacturing capacity of these chips, the silicon wafer, is huge. No company in this world is so naive or foolish to actually manufacture them without any kind of demand. Since there is a huge demand, all of them are manufacturing them in different flavors. So that speaks volumes. All the other talk that happens on the internet is all rubbish. You check out all the manufacturers, they don't write them as 8051s. If you see the data sheets, the core of it is 8051. So you check out Texas Instruments, you check out STM32. These are some of the big companies that I'm really talking about. You can check Renesas. You can check Silicon Labs. You can check NXP. All these are the biggies, the big brothers of the silicon industry. All of them manufacture them. It's just that you will not find a name by 8051 because now it's in the open domain. So this is very relevant. So if you have to really, if the need is not 32-bit, always go for an 8-bit. Because there are great advantages with 8-bit. There is the concept of this power consumption, the concept of making the system more reliable, the concept of making your code more reliable. All these go up to building such kind of systems. So it's just not that, just to make, just you feel that you need a 32-bit microcontroller for your system just to flaunt the ability of your system. It's not like that. It depends upon the use case. So you have to decide whether an 8-bit would suffice and look at the upgradability point of view for at least 10 years. What upgradabilities or what upgradations that you're expecting in your product in the next 10 years. Based on that, you have to make your decisions. So now let's get into the nitty-gritties of the code. So now this is called the Superloop architecture. Many of you are aware of this. It's a simple one. We have the main function, and we are calling a task X in it. And then we have this while one, which is called the super loop. Many people call this an infinite loop, but the better word is a super loop. Call it a super loop. And in this super loop, we are calling the task X. Now this task X is going to run endlessly, because while one means while true. So while it's true, it's going to run. So that true is not going to become false at any given point of time. So that's the reason the function X would be called continuously. So crucially, the super loop is an endless loop and is required because we have no operating system to return to. That means once your super loop starts, your program is all in that particular, that function X over here in this case, and it will keep looping through this function till the system power is removed. So there is no way to stop this. Once it enters that while one, that is the super loop, it will keep performing this task. This is the smallest embedded C program that you can really think of. Okay, and most of you know this. You must have used it at some point of time in your programming assignments, or for that matter, even at any point of time that you're designing something. So now, what are the strengths and weaknesses of super loops? Let's see the strengths. The main strength of the super loop system is their simplicity. There is nothing over here. This makes them easy to build, debug, test, and maintain. They are extremely efficient. They don't have any kind of hardware resource implications. There is no hardware involved over here. And they are highly portable. That means a super loop that is running on an ARM derivative and a super loop that is running on an 8051 are all going to be the same. You don't need to really make any changes. That's the reason they are extremely portable, is what we are saying. So if you're, but there are some issues associated with this. If your application requires accurate timing, for example, you need to acquire data precisely every 2 milliseconds, then this framework will not provide the accuracy or the flexibility that you require. Naturally not, because there is no way in which you can control the time. It just keeps running endlessly. So the basic super loop, and another big problem over here, you can say it's a disadvantage, is it operates at full power. That means it's in the normal operating mode at all times. It is not necessary that you run your program like this in most of the applications. And this can have an extremely dramatic impact on the system power consumption. That means how the system is going to use power. It's going to consume power constantly. So if you're going to use this kind of a design on a battery operated system, be ready for a battery drain in quick time. So this is not a good way of doing certain things. But as I said, they are simple, they are easy to build, they are debug, test, and maintain. They are extremely efficient and have minimal hardware resource implications, and they are highly portable. So now the trade-off is between the power, the timing accuracy, and the pros that we have already seen. Now you have to take the call what you want, but you should be aware of these facts when you are writing a code like this. And many a times the code is written like this. I'm pretty sure you can just give me a hands up. I would like to see how many of you really write it like this. Okay, 2 participants, 4, 5, 6, 7, 8, 9, 10. So the number is counting. That means I can understand many of you actually write it like this. So the numbers are just growing. So that is the biggest challenge that any system designer would face. How to actually control these things, especially the power consumption through software. So this is one thing that you really need to take care of. So Superloop is great, but it comes with these issues that you just saw. So now let's have a look at one simple example. Now we have a central heating controller over here. We have a temperature sensor that's connected to that controller. We have a temperature dial that's going to set up the temperature. And then we have a boiler over here that's actually going to start whenever the temperature goes down below a certain threshold based on the temperature sensed by the temperature sensor. And we have set up the temperature using the temperature dial. So if I'm going to create such a system, this is my general way of doing it. Like in the main function, I will first initialize whatever system, I mean, the peripherals that I want to initialize, or I want to set up some variables, or whatever system initialization routines that I want, I would do that initially the moment I enter into the main. And then I will create my super loop, and I'm going to call my functions, or these are tasks, you can say. So get required temperature, get actual temperature, then control the boiler. All these are different tasks that are going to run in my system, and I'm going to call in this super loop. Pretty straightforward, nothing different over here, and nothing wrong also. I mean, this system would certainly work. It is not wrong to have a system like this. So remember that we are doing this. We will see a slightly better way of doing it a little bit later. Now, when we are talking about 8051, we are actually going to use some ports with any microcontroller to really work with it, because some of the sensors or some of the external peripherals or switches would be connected to one of the port pins. So we'll just quickly brush through this, and if at all I want to read something from a port, first I have to initialize it to FF. That's how the 8051 works. And then I can read from the port. So using the port data is equal to P1 will allow me to read from that port. So if at all you want to just read one particular pin, you can set it up for reading a pin as well. So it's not just about the ports. Then we have some specific keywords that are there in Keil. We are going to use the Keil as our integrated development environment, and that is how we are going to proceed. And although, I mean, the world advocates about free and open source softwares, and that's the way forward. But let me tell you, when it comes to, critical embedded system design, where you have to prove the safety, the reliability aspects of your system, the open source softwares should be avoided, because there is no accountability, because you're dealing with human life. So in case there is a problem, there are legal implications on this. When you're creating a safety critical application, you are bound legally. And if there is a problem with your system and people are killed, you become answerable to the system, about the system design. So if at all you are using an open source software, and if there is a problem with the internal workings of those open source software, nobody is accountable over there. But when it comes to commercial softwares, like for example, if I'm using a commercial software from an XYZ company, and I have created a system and there is a catastrophic failure, not because of my design problems, but because of the inner workings of the tool that I use to make it. So I am not accountable for it. The company that made the tool and that declared that they conform to certain standards, they would be held accountable. So if you want to really make it very clear about who is accountable for the failure, it makes sense to actually use commercialized softwares. Otherwise, you have a lot of, you have the open source softwares in this domain as well, which you could use. But when it comes to safety, we are talking about safety critical designs. We are not talking about any embedded system. So we prefer using tools that are qualified internationally by international organizations. They have said that these tools are safe for use and they conform to those standards. Hence, you can use the tool with that guarantee that tomorrow, if there is a problem and some kind of a bug arises in the problem and can cause catastrophic failure and death of people, you will not be held responsible, provided your design is fine, but there is a problem with the inherent, the code of the tool. So that is the reason we are using Keil, which is the world leader in compiler design when it comes to such firmware based applications. So, and it is, of course, it is now a part of ARM, which is the father of most of these constrained devices today. So that's the architecture that you should be really working with, and not work with architectures like other architectures that are available generally. So so as to ensure that you have the best of all the worlds. So we are using Keil, the C51 compiler, and there is a free version that many of the educational institutes are using. So we will very much be in that zone. We will use that same one today also, and you can also use the same one. The C51 compiler, that is 2 KB code limited. And most of our code is extremely tiny, so it's more than sufficient. So here we have a number of defines that are actually setting up the constants, and now starts the real design aspects. These are small things, but they will go a long way in making your code extremely portable. I said that portability is the key. So when you're making safe, when you're designing code for safe systems, it should start at this level. So now what is this? We have a bunch of hash defines that we have shown over there. The reason for this is never use the port names straight away in your code. Like in, we are using your port 3. If I had used this directly in my code like this over here, what you can see, the disadvantage of this is not, this code is not portable. Because tomorrow, if I feel I want to switch over to, say, ARM, I will have to go at every line of my code in every file that I have and make these changes. But what if I have a define statement? I will just make the change over here in one file. So in place of P3, I may write some other port name that is existing in a different microcontroller that I'm going to use. So your portability issues start right over here. So this is the first aspect. And we are going to use the S-bit variables, which are proprietary to a Keel, because it makes your life easier. So these are actually, they will allow you to work at the bit level. The next thing that you can see over there, we have used that S-bit variable just to ensure that port 3 pin 0. So you can see it's LED port, and the caret symbol 0 means it's port 3 pin 0. So had I written P3 0, it could have been a different port, or if I had switched over to a different architecture. So once I define this, I can very well use this. Now I really don't need to change anything. If at all I port it to, say, an ARM derivative, I don't need to change the port pin's name over here, because if I change it over here, it automatically gets reflected over here. So that is the portability that you get. And this is just one line. Imagine you have a system that has about 1,000 lines of code, and every line you have to go and see where you need to make the changes. That's going to be extremely tedious job, and potential source of errors. So you should avoid that and start thinking about portability right from the word go. That is right from the first line. I'll show you some aspects of it when we actually run the code on Keel. So then we have another bunch of constants. Now one more thing over here. See what we have done. We are not going to use 0 and 1 directly in the code. Never do that. Instead, use constant names. So we are saying LED on is 0, LED off is 1. If you want to reverse the logic, you can easily change the logic over here. If you want LED on to be 1, LED off to be 0, you can do it over here. And most importantly, LED on, LED off will make it easier for you to read your code when you're actually writing it. So you know exactly what you're doing. If I had written warning LED is equal to 1 and warning LED is equal to 0, what sense it makes? I don't know what that 1 is. The logic could change at any given point of time as I change my families of microcontrollers. So this is extremely essential when you are going to make a reliable embedded system. Because see, if the logic changes, the entire functionality of your code changes. And that can be a potential source of confusion. And we are not talking about a single developer over there here. There is not just one person working on the code. There are n number of developers who are working across distributed time zones geographically. So they should, I mean, if there is uniformity right in the beginning, there is no source of confusion. And remember, you're working on a safety critical application, not on any embedded system. So all these things do matter when it comes to system design. The next thing, many a times you need to create a delay, because these are pretty common things that we generally use in any embedded system. See, of course, these things are not related to time triggered domains. We are talking in general about reliable systems, but ultimately we will be using time triggered systems to make these things. So these are some common things that are there in almost any kind of design, be it event triggered or time triggered. So if I want to create a simple delay without using any hardware timer, I can pretty well do this. It's simple. This delay is simple to implement. There is no hardware resource implication over here whatsoever. So if I just create a function like loop delay and I create some variables over here like X and Y, and I put a for loop and keep looping in over there. Since I'm using an 8051, the max value that I can put for the X is 65535, because after that it will loop back to 0, because it's basically we have 16-bit addresses, so it's going to loop back. So that's the max value that I can go through, and that's going to generate a max delay for me. What if I let's assume that we are working with a 12 megahertz crystal over here. So it's going to give me a 1 microsecond resolution for every increment of this for loop. I hope you understand that kind of calculation. So if it's a 12 megahertz clock, for every increment of this X, it's going to take around 1 microsecond. Approximately, it's what I assume. So what if I just have to have some, so the maximum value that I can get is over here 65 milliseconds. Let's assume it that way. What if I want something more? I can have nested loops like the one that you see on the right hand side, and I can keep nesting it further and further so that I can generate long and long and long delays. And this is the easiest way of doing it. Of course, it comes with a cost. The cost is you cannot precisely create these delays. You cannot say how much that 65535 is going to generate. What is the how is it, what is the time that it would take to go through that entire for loop? For that, you need to simulate the delay multiple times. And another problem that you will face is now you're working with a 12 megahertz and you have figured out a number by multiple simulations what delay you, I mean, what value you need to put for your X so as to generate, say, a 1 millisecond delay that you have figured out through multiple simulations for a 12 megahertz crystal. What if you change that crystal from 12 megahertz to 30 megahertz? Or rather the clock to any other frequency? Will that same value hold to generate the 1 millisecond delay that I generated using the current value? It will change. It cannot be the same because I changed the clock frequency. So you need to again simulate it to find out what would be the value that will generate 1 millisecond with 30 megahertz clock frequency that I'm using. So these delays need to be tweaked. Every time that you change a compiler, you change the clock frequency. So that's a task at hand. And even after doing that, you cannot get accurate delays. But one advantage that you get out of these delays is there is no hardware resource implication, no timer involved over here. But it comes with the cost of inaccuracy and the necessity to tweak it when you change the compiler, or even the same compiler, the compiler settings change, you change the clock frequency. That time you need to again rework these delays. I hope you understand that. Okay. So let's go a little bit further now. So we can create these software delays, which could be useful in many scenarios, but they are not, the accuracy is not guaranteed. So what are the strengths and weaknesses of these software only delays? Software delay can be used to produce very short delays. They require no hardware timers, and this delay will work on any microcontroller. See, there is no hardware specific that is there in this delay. It is only that you need to tweak them, or you say you need to change them whenever you change the family. But the basic structure of the loop remains the same. So they will work on any microcontroller, but you need to tweak it. What are the cons? It is difficult to produce precisely timed delays. The loops must be retuned if you decide to use a different processor, change the clock frequency, or even change the compiler optimization settings. So this comes with this price. But nonetheless, good for small delays, right? You have any questions you can put in the chat regarding what we have seen so far? Okay, I don't think so anybody has anything to ask. Let's move on now. Fine. So let me see if I can run some kind of a simple code before, so that you get a feel of what we're doing. Okay, so I'm just opening my Keel now. And just opening it up. Okay, let me just share the screen. Where is it on? Yeah. I'm just sharing the screen for, this is a simple program. Most of you know it, but I would just like to run this so that everybody is on the same page. Okay. I hope you can see my screen, all of you. The code part. Is it visible?
Yes, sir.
Yes, sir.
Yeah,
Yes.
great. So now we are into the Keel. I'm running the code limited, which you also can have. If you're running it, you can run it and just have a look at this. This is using the 8051 as the derivative, and we have created some function prototypes over here. We are using the s-bit variable and one bit variable, and just observe one thing. Look at the names, how they have been created. The way you create the function names, that also matters. Just don't haphazardly give names to your functions. When you're going to create a function, and just use the capital case, that is the uppercase for the actual name of the function, and the functionality is generally in the lowercase. These are some of the good coding practices that I am showing you at this point of time, because when it comes to safety and criticality, all these things matter to making the code adhere to those standards. And then you always have to define your function prototypes. And most importantly, now you can see we are using this unsigned int, but the new standard says that you should not use just unsigned int. You should use uint8 underscore t kind of the data types that have been suggested in the latest C99 standard. But we have kept this simple so that everybody understands the code, and we are not going to design any kind of a safety critical system over here. The basic idea over here is to make you understand what safety, reliability, and what time triggered really means. So certain things we have just neglected for the for this seminar, so that everybody understands it. Okay. So then we have, and look at this. This is the s-bit variable, which we are actually saying that this P1, port 1, pin 5 is called LED pin. So tomorrow, if I go port this to say an ARM derivative, this port number may change, this pin number may change. So if I change it over here, the rest of the code, I really don't need to touch at all. See, I'm not using anything that is specific to the family. It's just these names that I have created. So then we have the function prototypes here. And then our main function starts. We are initializing the function. And it's always good to make your code modular like this. Create functions so that they are actually tasks. So LED flash init is your function. And here, what it does. We are saying that there is a state variable that we have created. And it has been initialized to 0. So remember, we are not directly using the pin. We are creating a state variable. That's the difference. Otherwise, many of you would have really put up the pin straight away over here. Avoid doing that. Avoid doing that. We have created a state variable, and that we have set to 0. Then we have another variable that is LED flash change state. Now, if you look at this while loop, the super loop that we have, it is the normal thing that we do. So this is a normal program, the way we write it. So the first thing we do is we call the LED flash change state function. So what that function does, the functionality is over here. We are checking the state first. If the state is 1, we change the state to 0, and then we set the pin, rather clear the pin. We change the pin from high to low. But if the state was 0, we make the state 1, and then we make the pin, we set the pin. So this is a good way of writing a program for setting and resetting a pin. This is a simple LED blinking program, but look at the way it has been structured. The structure is critical. If the structure is not right, be ready for a rejection for your style of coding. And when the size of the code grows, this type of coding really helps. So follow these good practices. These are some good coding practices that you can certainly follow, and write it always like this. And then finally, what we have is we are calling a delay loop with the value 1000. Now this 1000, where is it? It's over here. So in the delay, we are putting that 1000, and this loop over here is going to generate about 1 millisecond delay. Now, many of you, I hope you can read this. Do you want me to increase the size of this? Is it readable?
Little bit, sir. Little bit. You can zoom to. It will be better.
Let me just see whether it gives me to zoom into this. Actually, I'm not able to zoom this after I have shared it. Can I really zoom into this?
It's okay, sir. Otherwise, it is visible. No problem. You can continue.
Because once I share it, it doesn't allow me to zoom into it. Let me
It's
just
okay.
check.
It's okay. It is visible, sir. No problem.
Yeah. So over here, this value 120. How has it come? I mean, I've just put 120, but if I run this, if you see, I'll just start running this. And okay, there it comes. And let me see if I can really show you something over here. Okay, I'll put a breakpoint here. And I'm running this. So I'm right over here. My program has stopped. I'll come over here. And let me just reset my timer. And see at the bottom over here, just keep an eye on this. It's all zeros over here. And I run this. See, it's almost 1 millisecond. It's 0.98. It's good enough accuracy for a software delay. So every time that I run this, it's going to come over there in about 0.98 seconds. So that's 1 milliseconds approximately. So what I'm trying to tell you is with this value of 120, I'm getting that 1 millisecond approximately. Now this 120 was arrived at by running through these simulations n number of times and then figuring out what the value should be over here. So there is no way in which you can determine this value through some mathematics or some logic. It's only by simulations. That's the best way of doing it. So this software delay loop is now giving me a value of about 1 millisecond. Now, if I remove this breakpoint over here and I run it in the free running mode, you can see that the LED is blinking over here in this portion. So that's actually blinking at a rate of around 1 millisecond. Okay. So if at all I have, let me see if I have the logic analyzer set up. No, it's not set. So if I just put the 1 minute. Yeah. Let me put the state. Oh, sorry, the bit. If at all, I just, yeah, there it is. So if I just stop this over here, you can see if I have my guiding lines, look at the delta. It's almost 0.977 and it's repeating. So one full cycle would be around 2 seconds. So that is how it is. So I have generated the delay that I want. So it's about 1000 milliseconds. That's about 1 second that I'm getting. So if I change this value over here, the loop execution time changes. And even if I change my derivative, I move to a different 8051 as well, this value will change, has to be tweaked. If I change my clock frequency, it has to be tweaked. If I change my compiler settings, it has to be tweaked. So this was a simple embedded program that you would generally write, but we have written it in a slightly more structured way, which is a good way of writing any embedded system program. Anybody has any questions on this program that we ran just now? It was a simple embedded system program that anybody would write. If you have any questions, you can put it up in the chat. Yeah, I think some.
So there are a few questions. Shall I read it for you?
Yeah, I am looking at it. Where is it now? This is regarding to your earlier session. What should be the time delay between consecutive interrupts and time triggered architecture? Actually, the standard time we are going to see that the standard ticks that are used, are generally 1 millisecond, but otherwise it is depending on what kind of tasks you have, how you want your tasks to be scheduled, and based on that, how many of them are really going to be repeated after what interval. All that determines your ticks in general. But the safest starting point would be 1 millisecond, but you should also consider the the HCF of or the GCD of all the different timings that you have before you decide on your tick interval. So that is how you generally decide on your tick interval. So that was that question. Then why do we need init function? Why don't we simply initialize directly? See, it is always good to initialize your system. As I said, make it modular. If you write directly within your while loop, your portability is lost, and you really don't know how your system is functioning. Everything should be broken down into modules, because you are creating a repository. You're not just one-off designer. We are talking about professional stuff over here. It's not about your, if at all you are still studying in college, you may just write it straight away. But whenever you are in that professional world, you are not the only one who is working. Make it modular, make your systems, you create your repository. Say you want to create a repository for ADC initialization. You just cannot directly put everything in one place. Create functions, and then you can make use of them in different projects. So that is the reason why we need to create this modularity. Okay. Then even hardware timers will require same amount of retuning, since registers might be different on porting. See, as I told you that when it comes to different families, different hardware timers have different way of initializations. So if at all you're going to use a different family altogether, naturally you have to do the retuning. I said that right in the beginning. Retuning is there when it comes to hardware specific usage. It's always there. But when we are talking about these software delays, the delay itself, that loop itself is portable, right? But the hardware timer is not portable, but the loop is portable. It's only that you need to retune them. That goes without saying. Okay. Then somebody said no, I don't know, probably does it create unnecessary execution delays if we have too many nested functions calling each other instead of directly putting the code there? Meaning, what do you mean by this, ma'am? This is Nisha Vasant asking this question. Could you just elaborate on this? Does it create unnecessary execution delays if we have too many nested functions calling each other instead of directly putting the code there? See, we are actually creating this delay so that we get the required delay beyond a certain point. If it's a 16-bit architecture over here, of course, 8051 is an 8-bit architecture, but it has got a 16-bit address space. So we can actually have 65,535 as the max value that can be stored over there. But if I want to generate larger delays, I will not be able to generate the larger delays. I will have to reduce the clock speed. But what if I don't want to reduce the clock speed? I have to go for nesting. Otherwise, I will not be able to generate longer delays, right? So we are generating that execution delay, as you said, because we want it. Okay, that's the reason we are nesting it, so that we can generate those huge delays. That was the basic idea, right? Yeah. Anything else? If you have anything more to ask about this last question that I can see, you can put it up in the chat. Okay, I don't think so. Fine. So that was as far as our.
Sir, actually, I saw that notification to unmute. What I meant is basically for that LED init code and LED change state code that we just saw. Basically, once we have more complex applications, there will be lots of such functions.
No, these function calls don't have any kind of bearing when it comes to modeling the system. Because when you're modeling the system, you have to take into account all this. And time-triggered architectures will allow you to account and be sure about how much time the function is really taking. you can really do your function profiling and find out how much time the function is taking to execute. That is how you're going to model your system.
Okay, so because even when I call a function, every time I call a function, it will have to change the address and go there. So
Yeah.
even that will add to whatever delay I'm counting.
Yeah, so all that has to be accounted for during the modeling stage. How much time your system is really taking. And with ARM architectures, they have something called as tail chaining. So it really doesn't, when you have multiple things called up in a sequence, they would be called up in quick succession. So there is very little, you can say latency when it comes to such kind of microcontrollers. Yeah. And this would really take care you have to take care of all this during the modeling phase. When you are actually creating functions, you should see how much time that function is taking for execution. Yeah. Fine. I think that should answer your question. If you still have anything, you can put it up in your chat box.
So one more question is there, I suppose.
I can't see it, sir. I can see the last thing is thank you, sir.
Which is better
Approach for TT system, hardware-based timer or software-based? See, I said I made this thing clear in the beginning. These software loops, they are good enough for creating small delays. But when you want accuracy, you should stay away from these software delay loops. You should then switch over to a timer. So a timer-based delay is always what I would really prefer. But yes, for small delays, where how much amount of time, the timing is not critical. You just need to spend an arbitrary amount of time within the larger time frame. Then it's fine for using software delays. That time it's okay. But otherwise, when it comes to extremely tight timing constraints, don't use software delays. Go in for hardware timers. Okay. Anything else? I think that is it. So what is the time? Shall we open up the quiz?
Yes, sir.
Yeah.
Rathod, sir.
Yes, we can. So you are this over, sir? Session over now, morning from your side?
Yeah, let's open up the quiz. It's not actually over. I have one more thing to really go
So
through.
shall we cover that in the afternoon?
Yeah, we'll cover it in the afternoon because
after Dr. Michael Pond's session,
yeah,
we'll cover that.
Dr. Michael Pond's session. That's fine because it's 12:40 almost. So
Yeah.
let's do the quiz.
Okay. So all of you, I'll put the link in the chat box. It's a simple Google form link. And I will keep those responses open exactly for 10 minutes. Once I put the link in the chat box, after that, you have to click that link and that Google form will open. You complete it, submit it. I will keep the responses open exactly for 10 minutes. Okay. So I'm giving you 2 minutes to settle down if you are not, so that I can put the link. Okay. And you are ready with that. And simple questions, very, very simple questions. Yeah, we just want to know whether you were attentive during the quiz or not, during the session or not. That's it. Not too difficult or anything. If you listen to what sir has said, you will be able to answer. And please join at 1:50 preferably, because yesterday Dr. Michael Pond, he already said that he's going to join 10-15 minutes before 2 o'clock and he wants to start the session exactly at 2 o'clock. So I request you to join 10 minutes early. So Govind sir, I'll put the link, okay?
Yeah. Go ahead, sir. And all the best, all of you. Do your best.
Done. So time starts now.
Yes, it's 12:40, 12:50 it will close.
Yes. Bhagat sir, you can also respond.
Yes, I'm
You
doing
can
that.
also attend.
Yes, sir, I'm doing that.
So try to score max in this. The second one will be even more technical. So you have to score 15 marks to qualify.
गोविंद सर,
Yeah, sir.
आपका कैमरा थोड़ा नीचे कीजिए.
वो एक्चुअली ग्लेयर आ रहा था उस पे, इसके लिए सर मैंने ऊपर
हाँ.
किया था उसको. ओके, आई एम सिटिंग नेक्स्ट टू द विंडो. फेस के ऊपर बहुत वाइट ये आ रहा था.
Correct, correct, correct. Good. Responses started receiving.
That's great to see some people have responded so quickly.
लेकिन ज्यादा जल्दी भी नहीं करनी चाहिए कभी कभी.
कुछ मिस आउट हो गया गलती से कुछ
10 minutes are there. Take your own 8 minutes.
There are 10 questions. You have 1 minute to think for the question.
Yes.
Rathod sir.
It's not a race. It's a 10 minutes quiz. Yes. Yes, sir.
Sir, the participants has to be told to go to the plenary section.
Yeah. That I know. I will. I know that. बोलेंगे. अच्छा आप ही बोलो ना. आप host हो.
So उसका time क्या है? 1:50 है ना?
1 o'clock to 1:30.
Okay.
And joining is on the inaugural link itself.
Yes. Somebody asking for putting this link in YouTube.
No, it is not allowed, and we will not
No,
recognize that. We will
they are
not
not
recognize that participant as a participant of this session. Only those who have joined this link meet here. Their attendance got registered in the Zoom. Only they are eligible for certificate and everything. That's
Right.
it. YouTube, nobody is eligible.
Excuse me, Rathod sir.
Yes. Who is
Yeah,
this?
yeah. My name is Gautam. I actually entered a different email than what I had registered for this call.
That is okay, but your name is there, no?
Yes, it is there.
Yeah.
Yeah, thank you.
Yes, you will be joining using the same link in the afternoon also. Okay. Dipti is asking. Yeah, Dipti. Sir, Anand sir, afternoon session, please join by 1:50. 2 o'clock sharp we will start. But there is a plenary session also at 1 o'clock. You are requested to join that as well, 1 to 1:30. Yes, sir, 1:50. You are correctly mentioned in the chat box. And I request all of you to be interactive in the afternoon session with the Dr. Pond. There is a raise hand symbol you can see near the chat box. You can click on that raise hand, and then our co-host Reena Madam and Bhagat sir, they are going to unmute you. You can ask the question. So question answer session will put at the end of his speech after 1 hour. Yeah, last 3 minutes remaining. So around 70% response is received from the attendees. So those who are not, make sure that you are submitting in the next 2 minutes. Yeah, many have responded. So last minute I'll close. ऐसा नहीं होना चाहिए कि मैंने क्लोज किया और उसके बाद आप सबमिट कर रहे हैं. So make sure that you are submitting before I click. I think only 1 or 2 people are remaining. So I'm still waiting for a few seconds. Because almost more than 60 people have responded. Okay, I'll close. Yeah, done.
Great. So we will be back at 1:50.
Yeah, so thank you very much, everybody. And now there is a plenary talk. You can see the details on the conference website as well. And the joining link for the plenary talk will be the same as inaugural link. You are most welcome to join that in a plenary talk. It's only for half an hour. You can join it. And you can proceed for your lunch from 1:30 to 2 o'clock. But my sincere request is please be on the same link, this link at 1:50. Okay. So thank you very much. Thanks a lot.
Thank you so much.
Thank you, sir.
Okay.
Sir, live.
Yes, sir. Yeah, you can close.
Yeah.
Reena, madam.
Yes,
Madam.
yes, I'll stop the recording.
Yeah.
Okay.